Lambda calculus is a formal system in mathematical logic and computer science for expressing computation based on function abstraction and application using variable binding and substitution. First formulated by Alonzo Church to formalize the concept of effective computability, lambda calculus found early successes in the area of computability theory, such as a negative answer to Hilbert's Entscheidungsproblem. Lambda calculus is a conceptually simple universal model of computation. The name derives from the Greek letter lambda used to denote binding a variable in a function. Because of the importance of the notion of variable binding and substitution, there is not just one system of lambda calculus, and in particular there are typed and untyped variants. Historically, the most important system was the untyped lambda calculus, in which function application has no restrictions. In the Church-Turing Thesis, the untyped lambda calculus is claimed to be capable of computing all effectively calculable functions. The typed lambda calculus is a variety that restricts function application, so that functions can only be applied if they are capable of accepting the given input's type of data. Today, the lambda calculus has applications in many different areas in mathematics, philosophy, linguistics, and computer science. It is still used in the area of computability theory, although Turing machines are also an important model for computation. Lambda calculus has played an important role in the development of the theory of programming languages. Counterparts to lambda calculus in computer science are functional programming languages, which essentially implement the lambda calculus. Beyond programming languages, the lambda calculus also has many applications in proof theory. A major example of this is the Q-Howard correspondence, which gives a correspondence between different systems of typed lambda calculus and systems of formal logic. Lambda calculus in the history of mathematics. The lambda calculus was introduced by mathematician Alonzo Church in the 1930s as part of an investigation into the foundations of mathematics. The original system was shown to be logically inconsistent in 1935 when Stephen Kleene and J.B. Rosset developed the Kleene-Rosset paradox. Subsequently, in 1936 Church isolated and published just the portion relevant to computation, what is now called the untyped lambda calculus. In 1940, he also introduced a computationally weaker, but logically consistent system, known as the simply typed lambda calculus. In formal description, motivation, computable functions are a fundamental concept within computer science and mathematics. The I-calculus provides a simple semantics for computation, enabling properties of computation to be studied formally. The I-calculus incorporates two simplifications that make this semantic simple. The first simplification is that the I-calculus treats functions anonymously, without giving them explicit names. For example, the function can be rewritten in anonymous form as read as the pair of and is mapped to. Similarly, can be rewritten in anonymous form as where the input is simply mapped to itself. The second simplification is that the I-calculus only uses functions of a single input. An ordinary function that requires two inputs, for instance the function, can be reworked into an equivalent function that accepts a single input, and as output returns another function, that in turn accepts a single input. For example, can be reworked into. This method, known as currying, transforms a function that takes multiple arguments into a chain of functions each with a single argument. Function application of the function to the arguments yields at once. Whereas evaluation of the curried version requires one more step to arrive at the same result. The lambda calculus. The lambda calculus consists of a language of lambda terms, which is defined by a certain formal syntax, and a set of transformation rules, which allow manipulation of the lambda terms. These transformation rules can be viewed as an equational theory or as an operational definition. As described above, all functions in the lambda calculus are anonymous functions, having no names. They only accept one input variable, with currying used to implement functions with several variables. Lambda terms. The syntax of the lambda calculus defines some expressions as valid lambda calculus expression and some as invalid, just as some strings of characters are valid C programs and some are not. A valid lambda calculus expression is called a lambda term. The following three rules give an inductive definition that can be applied to build all syntactically valid lambda terms. A variable is itself a valid lambda term, if is a lambda term, and is a variable, then is a lambda term. If and are lambda terms, then is a lambda term. Nothing else is a lambda term. Thus a lambda term is valid if and only if it can be obtained by repeated application of these three rules. However, some parentheses can be omitted according to certain rules. For example, the outermost parentheses are usually not written. A lambda abstraction is a definition of an anonymous function that is capable of taking a single input and substituting it into the expression. It thus defines an anonymous function that takes x and returns t. For example, is a lambda abstraction for the function using the term for t. The definition of a function with a lambda abstraction merely sets up the function but does not invoke it. The abstraction binds the variable in the term. An application represents the application of a function to an input, that is, it represents the act of calling function t on input s to produce. There is no concept in lambda calculus of variable declaration. In a definition such as, the lambda calculus treats y as a variable that is not yet defined. The lambda abstraction is syntactically valid, and represents a function that adds its input to the yet unknown y. Bracketing may be used and may be needed to disambiguate terms. For example, and denote different terms. Functions that operate on functions. In lambda calculus, functions are taken to be first-class values, so functions may be used as the inputs, or be returned as outputs from other functions. For example, represents the identity function, and represents the identity function applied to. Further, represents the constant function, the function that always returns, no matter the input. In lambda calculus, function application is regarded as left associative, so that means. There are several notions of equivalence and reduction that allow lambda terms to be reduced to equivalent lambda terms. Alpha equivalence, a basic form of equivalence, definable on lambda terms, is alpha equivalence. It captures the intuition that the particular choice of a bound variable, in a lambda abstraction, does not matter. For instance, and are alpha equivalent lambda terms, and they both represent the same function. The terms and are not alpha equivalent, because they are not bound in a lambda abstraction. In many presentations, it is usual to identify alpha equivalent lambda terms. The following definitions are necessary in order to be able to define beta reduction. Free variables. The free variables of a term are those variables not bound by a lambda abstraction. The set of free variables of an expression is defined inductively. The free variables of a just, the set of free variables of is the set of free variables of, but with removed, the set of free variables of are the union of the set of free variables of and the set of free variables of. For example, the lambda term representing the identity has no free variables, but the function has a single free variable. Capture avoiding substitutions, suppose, and are lambda terms and are variables. The notation indicates substitution of for in a capture avoiding manner. This is defined so that if and is not in the free variables of, the variable is said to be fresh for. For example, and. The freshness condition is crucial in order to ensure that substitution does not change the meaning of functions. For example, a substitution is made that ignores the freshness condition. This substitution turns the constant function into the identity by substitution. In general, failure to meet the freshness condition can be remedied by alpha renaming with a suitable fresh variable. For example, switching back to our correct notion of substitution, in the lambda abstraction can be renamed with a fresh variable, to obtain, and the meaning of the function is preserved by substitution. Beta reduction. The beta reduction rule states that an application of the form reduces to the term. The notation is used to indicate that beta reduces to. For example, for every. This demonstrates that really is the identity. Similarly, which demonstrates that is a constant function. the Lambda calculus may be seen as an idealized functional programming language, like Haskell or Standard Mill. Under this view, beta reduction corresponds to a computational step. This step can be repeated by additional beta conversions until there are no more applications left to reduce. In the untyped Lambda calculus, as presented here, this reduction process may not terminate. For instance, consider the term here. That is, the term reduces to itself in a single beta reduction, and therefore the reduction process will never terminate. Another aspect of the untyped Lambda calculus is that it does not distinguish between different kinds of data. For instance, it may be desirable to write a function that only operates on numbers. However, in the untyped Lambda calculus, there is no way to prevent a function from being applied to truth values, strings, or other non-number objects. Formal definition. Lambda expressions are composed of variables v1, v2, vn. The abstraction symbols lambda I and ... parentheses, the set of lambda expressions, I, can be defined inductively. If x is a variable, then xai, if x is a variable and mai, then ai, if m, nai, then ai. Instances of Rule 2 are known as abstractions and instances of Rule 3 are known as applications. Notation. To keep the notation of lambda expressions uncluttered, the following conventions are usually applied. Outermost parentheses are dropped, mn instead of, applications are assumed to be left associative, mnp may be written instead of p, the body of an abstraction extends as far right as possible, ix. mn means ix. mn, and not n, a sequence of abstractions is contracted, ixoyiz. N is abbreviated as x's. N, free and bound variables, the abstraction operator, I, is said to bind its variable wherever it occurs in the body of the abstraction. Variables that fall within the scope of an abstraction are said to be bound. All other variables are called free. For example, in the following expression y is a bound variable and x is free, iyxxy. Also note that a variable is bound by its nearest abstraction. In the following example the single occurrence of x in the expression is bound by the second lambda, ixy, the set of free variables of a lambda expression, m, is denoted as fe, m, and is defined by recursion on the structure of the terms, as follows, fe, x, equals x, where x is a variable, fe, ix. M, equals fe, m, x, fe, mn, equals fe, m, and fe, n. An expression that contains no free variables is said to be closed. Closed lambda expressions are also known as combinators and are equivalent to terms in combinatory logic. Reduction. The meaning of lambda expressions is defined by how expressions can be reduced. There are three kinds of reduction: I plus or minus conversion, changing bound variables; I squared reduction, applying functions to their arguments; I conversion, which captures a notion of extensionality. We also speak of the resulting equivalences. Two expressions are I squared equivalent, if they can be I squared converted into the same expression, and I plus or minus / I equivalents are defined similarly. The term regex, short for reducible expression, refers to subterms that can be reduced by one of the reduction rules. For example, n is a beta regex in expressing n is substituted for x in m. If x is not free in m, ix. mx is an eta regex. The expression to which a regex reduces is called its reduct. Using the previous example, the reducts of these expressions are respectively m, x, equals n, and m, I plus or minus conversion. Alpha conversion, sometimes known as alpha renaming, allows bound variable names to be changed. For example, alpha conversion of ixx might yield iyy. Terms that differ only by alpha conversion are called I plus or minus equivalent. Frequently in uses of lambda calculus, I plus or minus equivalent terms are considered to be equivalent. The precise rules for alpha conversion are not completely trivial. First, when alpha converting an abstraction, the only variable occurrences that are renamed are those that are bound to the same abstraction. For example, an alpha conversion of ixixx could result in iyyxx, but it could not result in iyyxy. The latter has a different meaning from the original. Second, alpha conversion is not possible if it would result in a variable getting captured by a different abstraction. For example, if we replace x with y and ixiyx, we get iyyy, which is not at all the same. In programming languages with static scope, alpha conversion can be used to make name resolution simpler by ensuring that no variable name masks a name in a containing scope. Substitution, written e, var equals r, is the process of replacing all free occurrences of the variable v in the expression e with expression a substitution on terms of the I calculus is defined by recursion on the structure of terms, as follows. X, za equals n, a per mil n, y, za equals n, a per mil y, if x a per mil y, m1 m2, za equals n, a per mil, ix. M, za equals n, a per mil ix. M, iy. M, za equals n, a per mil iy. M, za equals n, if x a per mil y, provided y a per mil fe, n. To substitute into a lambda abstraction, it is sometimes necessary to I plus or minus convert the expression. For example, it is not correct for y equals x to result in, because the substituted x was supposed to be free but ended up being bound. The correct substitution in this case is, up to I plus or minus equivalence. Notice that substitution is defined uniquely up to I plus or minus equivalence. I-squared reduction, beta reduction captures the idea of function application. Beta reduction is defined in terms of substitution, the beta reduction of AIVE, a euro squared a is e, var equals a euro squared. For example, assuming some encoding of 2, 7, a, we have the following I-squared reduction, 7, a 7a, 2. I conversion. Eta conversion expresses the idea of extensionality, which in this context is that two functions are the same if and only if they give the same result for all arguments. Eta conversion converts between ix, fx, and f whenever x does not appear free in f. Normal forms and confluence. For the untyped lambda calculus, I-squared reduction as a rewriting rule is neither strongly normalizing nor weakly normalizing. However, it can be shown that I-squared reduction is confluent. Therefore, both strongly normalizing terms and weakly normalizing terms have a unique normal form. For strongly normalizing terms, any reduction strategy is guaranteed to yield the normal form, whereas for weakly normalizing terms, some reduction strategies may fail to find it. Encoding data types. The basic lambda calculus may be used to model Booleans, arithmetic, data structures and recursion, as illustrated in the following subsections. Arithmetic in lambda calculus. There are several possible ways to define the natural numbers in lambda calculus, but by far the most common are the Church numerals, which can be defined as follows: 0 equals ifixx, 1 equals ifixfx, 2 equals ifixf, 3 equals ifixf, and so on. Or using the alternative syntax presented above in notation, 0 equals ifxx, 1 equals ifxfx, 2 equals ifxf, 3 equals ifxf. A Church numeral is a higher-order function it takes a single-argument function f, and returns another single-argument function. The Church numeral n is a function that takes a function f as argument and returns the nth composition of f, that is the function f composed with itself n times. This is denoted f, n, and is in fact the nth power of f. f0 is defined to be the identity function. Such repeated compositions obey the laws of exponents, which is why these numerals can be used for arithmetic. We can define a successor function, which takes a number n and returns n plus 1 by adding an additional application of f, where mf, x means the function f is applied m times on x, succ equals inifixf. because the mth composition of f composed with the nth composition of f gives the m plus nth composition of f, addition can be defined as follows: plus equals iminifixmf, plus can be thought of as a function taking two natural numbers as arguments and returning a natural number. It can be verified that plus 2, 3 and 5 are equivalent lambda expressions. Since adding m to a number n can be accomplished by adding 1 m times, an equivalent definition is plus equals iminmsucc na euro. Similarly, multiplication can be defined as multa equals iminifm, alternatively, multa equals iminm0, since multiplying m and n is the same as repeating the add n function m times and then applying it to 0. Exponentiation has a rather simple rendering in Church numerals, namely, power equals IBIEEB, the predecessor function defined by PREDN equals NA1 for a positive integer n and PRED0 equals 0 is considerably more difficult. The formula, PRED equals INIFIXN, can be validated by showing inductively that if T denotes, then T, N, IUX, equals, x for n greater than 0. Two other definitions of PRED are given below, one using conditionals and the other using pairs. With the predecessor function, subtraction is straightforward. Defining, sub equals IMINNPREDM, sub mn yields MAN when m, n and 0 otherwise. Logic and predicates, by convention, the following two definitions are used for the Boolean values true and false. True E equals IXOYX, false E equals IXOYY. Note that false is equivalent to the Church numeral 0 defined above. Then, with these two I terms, we can define some logic operators, and A equals IPIQPQP, or A equals IPIQPPQ, note A equals IPIAIBPB. If then else E equals IPIAIBPAB, we are now able to compute some logic functions. For example, and true-false, a permil true-false AI squared true-false true, a permil false true AI squared false. And we see that and true-false is equivalent to false. A predicate is a function that returns a Boolean value. The most fundamental predicate is is0, which returns true if its argument is the Church numeral 0, and false if its argument is any other Church numeral, is equals INN true. The following predicate tests whether the first argument is less than or equal to the second, lec equals IMIN. Is 0, and since m equals n, if leqmn and leqnm, it is straightforward to build a predicate for numerical equality. The availability of predicates and the above definition of true and false make it convenient to write if-then-else expressions in lambda calculus. For example, the predecessor function can be defined as PRED equals INNK10, which can be verified by showing inductively that NK1 is the add NA1 function for n greater than 0. Pairs, a pair can be defined in terms of true and false, by using the Church encoding for pairs. For example, PAIR encapsulates the pair, first returns the first element of the pair, and second returns the second. PIRA equals IXOYIFFXY, first A equals IPP true, second A equals IPP false, nil equals IX. True, null equals IPP. A linked list can be defined as either NIL for the empty list, or the PAIR of an element and a smaller list. The predicate null tests for the value NIL obviates the need for an explicit null test. As an example of the use of pairs, the shift and increment function that maps to can be defined as I equals IX. PAIR, which allows us to give perhaps the most transparent version of the predecessor function, PRED equals IN. First, recursion and fixed points. Recursion is the definition of a function using the function itself. On the face of it, lambda calculus does not allow this. However, this impression is misleading. Eine Euro y a Euro both a Euro s refer to the same lambda term, y, so it is possible for a lambda expression a Euro here y a Euro to be arranged to receive itself as its argument value, through self-application. Consider for instance the factorial function f, n, recursively defined by f, n equals 1, if n equals 0. Else n f, na1. In the lambda expression which is to represent this function, a parameter will be assumed to receive the lambda expression itself as its value, so that calling it applying it to an argument will amount to recursion. Thus to achieve recursion, the intended as self-referencing argument must always be passed to itself within the function body, at a call point, GA equals IR. In 1, if n equals 0. Else na. With a or rx equals fx equals grx a to hold, so or equals g a and far equals gg equals g, the self-application achieves replication here, passing the function's lambda expression onto the next invocation as an argument value, making it available to be referenced and called there. This solves it but requires rewriting each recursive call as self-application. We would like to have a generic solution, without a need for any rewrites, GA equals IR. In 1, if n equals 0. Else na. With a or x equals fx equals grx a to hold, so or equals gr equals fix g a and far equals fix g a here fix gar equals g. So theta fix g equals. Given a lambda term with first argument representing recursive call, the fixed point combinator fix will return a self-replicating lambda expression representing the recursive function. The function does not need to be explicitly passed to itself at any point, for the self-replication is arranged in advance, when it is created, to be done each time it is called. Thus the original lambda expression is recreated inside itself, at call point, achieving self-reference. In fact, there are many possible definitions for this fix operator, the simplest of them being, ya equals ig. Ixg, in the lambda calculus, y-gar is a fixed point of g, as it expands to, yg, ih. Ixhg, ixg, g. Now, to perform our recursive call to the factorial function, we would simply call n, where n is the number we are calculating the factorial of. Given n equals 4, for example, this gives yg, 4, g4, irin. 1, if n equals 0. Else na, 4, in. 1, if n equals 0. Else na, 4, 1, if 4 equals 0. Else 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 24, every recursively defined function can be seen as a fixed point of some suitably defined function closing over the recursive call with an extra argument, and therefore, using y, every recursively defined function can be expressed as a lambda expression. In particular, we can now cleanly define the subtraction, multiplication and comparison predicate of natural numbers recursively. Standard terms: certain terms have commonly accepted names, ia equals ixx, chi equals ixoyx, za equals ixoyizxz, bar equals ixoyizx, chi equals ixoyizxzy, y equals ixoyxyy, way equals ixxx, ipermil equals ixxx, I equals ipermil, ya equals ig. Ixg, typed lambda calculi. A typed lambda calculus is a typed formalism that uses the lambda symbol to denote anonymous function abstraction. In this context, types are usually objects of a syntactic nature that are assigned to lambda terms. The exact nature of a type depends on the calculus considered. From a certain point of view, typed lambda calculi can be seen as refinements of the untyped lambda calculus, but from another point of view, they can also be considered the more fundamental theory and untyped lambda calculus a special case with only one type. Typed lambda calculi are foundational programming languages and are the base of typed functional programming languages such as ML and Haskell and, more indirectly, typed imperative programming languages. Typed lambda calculi play an important role in the design of type systems for programming languages. Here typeability usually captures desirable properties of the program, For example, the program will not cause a memory access violation. Typed lambda calculi are closely related to mathematical logic and proof theory via the Kuo-Howard isomorphism, and they can be considered as the internal language of classes of categories. For example, the simply typed lambda calculus is the language of Cartesian closed categories. Computable functions and lambda calculus. A function f, n of natural numbers is a computable function if and only if there exists a lambda expression f such that for every pair of x, y and n, f, x, equals y if and only if f za equals I squared ay, where x and y are the Church numerals corresponding to x and y, respectively, and equals I squared meaning equivalence with beta reduction. This is one of the many ways to define computability. See the Church Turing Thesis for a discussion of other approaches and their equivalents. Undecidability of equivalence. There is no algorithm that takes as input two lambda expressions and outputs true or false depending on whether or not the two expressions are equivalent. This was historically the first problem for which undecidability could be proven. As is common for a proof of undecidability, the proof shows that no computable function can decide the equivalence. Church's thesis is then invoked to show that no algorithm can do so. Church's proof first reduces the problem to determining whether a given lambda expression has a normal form. A normal form is an equivalent expression that cannot be reduced any further under the rules imposed by the form. Then he assumes that this predicate is computable, and can hence be expressed in lambda calculus. Building on earlier work by Kleene and constructing a GAR paragraph del numbering for lambda expressions, he constructs a lambda expression E that closely follows the proof of GAR paragraph del's first incompleteness theorem. If E is applied to its own GAR paragraph del number, a contradiction results. Lambda calculus and programming languages. As pointed out by Peter Landin's 1965 paper A Correspondence between ALGOL 60 and Church's lambda notation, sequential procedural programming languages can be understood in terms of the lambda calculus, which provides the basic mechanisms for procedural abstraction and procedure application. Lambda calculus reifies functions, and makes them first-class objects, which raises implementation complexity when it is implemented. Anonymous functions. For example, in Lisp the square function can be expressed as a lambda expression as follows. The above example is an expression that evaluates to a first-class function. The symbol lambda creates an anonymous function, given a list of parameter names, just a single argument in this case, and an expression that is evaluated as the body of the function. The Haskell example is identical. Anonymous functions are sometimes called lambda expressions. For example, Pascal and many other imperative languages have long supported passing subprograms as arguments to other subprograms through the mechanism of function pointers. However, function pointers are not a sufficient condition for functions to be first-class data types, because a function is a first-class data type if and only if new instances of the function can be created at runtime. And this runtime creation of functions is supported in Smalltalk, JavaScript, and more recently in Scala, Eiffel, C and C++11, among others. Reduction strategies. Whether a term is normalizing or not, and how much work needs to be done in normalizing it if it is, depends to a large extent on the reduction strategy used. The distinction between reduction strategies relates to the distinction in functional programming languages between eager evaluation and lazy evaluation. Full beta reductions. Any regex can be reduced at any time. This means essentially the lack of any particular reduction strategy with regard to reducibility. All bets are off. Applicative order. The leftmost, innermost regex is always reduced first. Intuitively, this means a function's arguments are always reduced before the function itself. Applicative order always attempts to apply functions to normal forms, even when this is not possible. Most programming languages are described as strict, meaning that functions applied to non-normalizing arguments are non-normalizing. This is done essentially using applicative order, called by value reduction, but usually called eager evaluation. Normal order. The leftmost, outermost regex is always reduced first. That is, Whenever possible, the arguments are substituted into the body of an abstraction before the arguments are reduced. Call by name, as normal order, but no reductions are performed inside abstractions. For example, ix. Ixx, x is in normal form according to this strategy, although it contains the regex. Call by value, only the outermost regexes are reduced. A regex is reduced only when its right-hand side has reduced to a value. Called by need, as normal order, but function applications that would duplicate terms instead name the argument, which is then reduced only when it is needed. Called in practical contexts lazy evaluation. In implementations, this name takes the form of a pointer, with a regex represented by a thunk. Applicative order is not a normalizing strategy. The usual counterexample is as follows: define I copyright equals I permil where I permil equals ixxx. This entire expression contains only one regex, namely the whole expression. Its reduct is again I copyright. Since this is the only available reduction, I copyright has no normal form. Using applicative order, the expression key copyright equals I copyright is reduced by first reducing I copyright to normal form, but since I copyright has no normal form, applicative order fails to find a normal form for key copyright. In contrast, normal order is so called because it always finds a normalizing reduction, if one exists. In the above example, key copyright reduces under normal order to I, a normal form. A drawback is that regexes in the arguments may be copied, resulting in duplicated computation reduces toy, y, using this strategy. Now there are two regexes, so full evaluation needs two more steps, but if the argument had been reduced first, there would now be none. The positive trade-off of using applicative order is that it does not cause unnecessary computation, if all arguments are used, because it never substitutes arguments containing regexes and hence never needs to copy them. In the above example, in applicative order, reduces first toy and then to the normal order of, taking 2 steps instead of 3. Most purely functional programming languages, and the proof languages of theorem provers, use lazy evaluation, which is essentially the same as call by need. This is like normal order reduction, but call by need manages to avoid the duplication of work inherent in normal order reduction using sharing. In the example given above, y reduces toy, y, which has 2 regexes, but in call by need they are represented using the same object rather than copied, so when one is reduced the other is too. A note about complexity: while the idea of beta reduction seems simple enough, it is not an atomic step, in that it must have a non-trivial cost when estimating computational complexity. To be precise, one must somehow find the location of all of the occurrences of the bound variable v in the expression e, implying a time cost, or one must keep track of these locations in some way, implying a space cost. A Norvay search for the locations of v in e is O, n, in the length n of e. This has led to the study of systems that use explicit substitution. Synod's director strings offer a way of tracking the locations of free variables in expressions. Parallelism and concurrency: the Church-Rosset property of the Lambda calculus means that evaluation can be carried out in any order, even in parallel. This means that various non-deterministic evaluation strategies are relevant. However, the Lambda calculus does not offer any explicit constructs for parallelism. One can add constructs such as futures to the Lambda calculus. Other process calculi have been developed for describing communication and concurrency. Semantics: the fact that Lambda calculus terms act as functions on other Lambda calculus terms, and even on themselves, led to questions about the semantics of the Lambda calculus. Could a sensible meaning be assigned to Lambda calculus terms? The natural semantics was to find a set D isomorphic to the function space D of functions on itself. However, no non-trivial such D can exist, by cardinality constraints, because the set of all functions from D into D has greater cardinality than D. In the 1970s, Dana Scott showed that, if only continuous functions were considered, a set or domain D with the required property could be found, thus providing a model for the Lambda calculus. This work also formed the basis for the denotational semantics of programming languages. See also. References. Further reading, Abelson, Harold and Gerald J. Sussman. Structure and Interpretation of Computer Programs. The MIT Press. ISBN 0-262-51087-1. Hendrik Peter Berendt Introduction to Lambda Calculus. Henk Berendt, The Impact of the Lambda Calculus in Logic and Computer Science. The Bulletin of Symbolic Logic, Volume 3, Number 2, June 1997. Berendt, Hendrik Peter, The Type-Free Lambda Calculus pp 1091 €1132 of Handbook of Mathematical Logic, North Holland ISBN 0-7204-2285-X, Cardoni and Hindley, 2006. History of Lambda Calculus and Combinatory Logic. In Gubbay and Woods, Handbook of the History of Logic, Volume 5. Elsevier. Church, Alonzo, An Unsolvable Problem of Elementary Number Theory, American Journal of Mathematics, 58, pp. 345 €363. This paper contains the proof that the equivalence of lambda expressions is in general not decidable. Klein, Stephen, A Theory of Positive Integers in Formal Logic, American Journal of Mathematics, 57, pp. 153 €173 and 219 €244. Contains the lambda calculus definitions of several familiar functions. Landon, Peter, A Correspondence between ALGOL 60 and Church's Lambda Notation, Communications of the ACM, Volume 8, Number 2, pages 89 €101. Available from the ACM site. A classic paper highlighting the importance of lambda calculus as a basis for programming languages. Larson, Jim, An Introduction to Lambda Calculus and Scheme. A Gentle Introduction for Programmers. Schuck, A. and Simmons, H. An Introduction to iCalculi and Arithmetic with a Decent Selection of Exercises. Notes for a Course in the Mathematical Logic MSc at Manchester University, De Queiroz, Raj G. B. On Reduction Rules, Meaning as Use and Proof Theoretic Semantics. Studia Logica, 92, 211-247. A paper giving a formal underpinning to the idea of meaning as use which, even if based on proofs, it is different from proof theoretic semantics as in the Dummeke-Prawitz tradition since it takes reduction as the rules giving meaning. Monographs Textbooks for Graduate Students, Morton Heine-Zal Rentzen, Poyer Zichin, Lectures on the Curry-Howard Isomorphism, Elsevier, 2006, ISBN 0-444-52077-5 is a recent monograph that covers the main topics of lambda calculus from the type-free variety, to most typed lambda calculi, including more recent developments like pure type systems and the lambda cube. It does not cover subtyping extensions. Pierce, Benjamin, Types and Programming Languages, MIT Press, ISBN A0-262-16209-1. Covers lambda calculi from a practical type system perspective. Some topics like dependent types are only mentioned, but subtyping is an important topic. Some parts of this article are based on material from FOLDOC, used with permission. External links, Haswinkel, Michiel, ed., Lambda Calculus, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Achim-Ewing, A Short Introduction to the Lambda Calculus, PDF, Dana Scott, A Timeline of Lambda Calculus, PDF, David C. Keenan, To Dissect a Mockingbird, A Graphical Notation for the Lambda Calculus with Animated Reduction, Raw L. Rojas. A Tutorial Introduction to the Lambda Calculus, PDF, Peter Salinger, Lecture Notes on the Lambda Calculus, PDF, L. Allison, Some Executable iCalculus Examples, Georg P. Lichczewski, The Lambda Calculus. And A++, Brett Victor, Alligator Eggs, A Puzzle Game Based on Lambda Calculus. Lambda Calculus on Cefalra Euro unregistered trademark S website, Lambda Calculus at planetmath.org. LCI Lambda Interpreter, a simple yet powerful pure calculus interpreter. Lambda Calculus links on Lambda the Ultimate, Mike the, Lambda Animator, a graphical Java applet demonstrating alternative reduction strategies. An Introduction to Lambda Calculus and Scheme, by Jim Larson, implementing the Lambda Calculus using C++ templates, Marius Buliga, Graphic Lambda Calculus. Lambda Calculus is a workflow model by Peter Kelly, Paul Coddington, and Andrew Wendelben. Mentions graph reduction as a common means of evaluating lambda expressions and discusses the applicability of lambda calculus for distributed computing. Shane Steinert Throkeld, Lambda Calculi, Internet Encyclopedia of Philosophy.